The broadcast is now starting. All attendees are in listen-only mode.
Hi everyone, thanks for joining our webinar on ePMP technologies. I'm your host Colin Hyduk, and my special guest today is the product line manager of our ePMP, and that is Alex Marcham. So as always, if you have any questions, please type them into the text box on the right, and we will get to them throughout the presentation or at the end. And so without further ado, here's Alex.
Hi everyone. So I thought what we'd have a little look through today is some of the ePMP technologies, both some you may be familiar with already and some that may be new. So let's get started. So ePMP really is designed as a low-cost fixed wireless access platform in unlicensed 2.4 and 5 gigahertz spectrum to take you from a network that looks something like the one on the left here, where the guy's having difficulty scaling. Oh, sorry, didn't realize we weren't showing the screen. My apologies. So hopefully you can see the network on the left now. Technology, as ever, remains a mystery. So the network on the left is basically started out as a point-to-multipoint network, but over the years, the operator has had trouble scaling, and he has had to start putting in multiple point-to-point dishes, and that increases both the amount of interference in his network and surrounding networks, but also, as you can see, makes troubleshooting rather a pain. So what ePMP is designed to do is, for a very comparable price, get you from something that looks like the network on the left to something that looks like the one on the right. So the network on the right is a GPS synchronized ePMP setup with up to 360 concurrent users connected, as we have 3 access points there, delivering far more capacity and connected customers than the network on the left, whilst being much easier to troubleshoot. So a little bit about how we go from the network on the left to the network on the right. Sorry, still waiting to view the screen. Do you want to?
Yeah, let me see. Should be working on my end. Working now. Okay, it was just a little delayed. Perfect.
Thank you for letting us know, by the way. So some of the key applications for something like ePMP. So high-density enterprise access. These are things like either internet access to enterprise assets or buildings, or things like inter-building connections on a business park, for example. Also includes the application that ePMP is probably best known for, which is cost-effective, primarily residential internet coverage in rural areas and semi-rural areas. We also see a lot of usage for video surveillance, and I'll go into a bit more detail about this specific use case because it brings up some interesting things about ePMP technology. And Wi-Fi backhaul. You can see there that on that street light there is an ePMP subscriber module at the top, providing backhaul for the Wi-Fi access point below it, which is about halfway down the pole, which makes it very easy to easily deploy Wi-Fi wherever you need to. So the reason why we're able to provide some of these demanding applications over some very low-cost equipment in ePMP is through technology that we call primarily eFortify. So eFortify is really designed to increase the interference tolerance of your network. So we're talking about operating in unlicensed spectrum, so as long as they abide by the local regulatory rules, or even not in some cases, as I'm sure some of you have seen, anyone can pitch up and begin transmitting on that entire unlicensed spectrum band, whether 2.4 or 5 gigahertz, and possibly create a lot of interference for your network, which degrades your ability to provide adequate service to your customers. So eFortify is a set of technologies, as you can see there, to provide high performance and consistent latency under external interference. So another aspect of performance in real-world conditions that we address through ePMP technology is GPS synchronization. And I've got a bit more about each of these as we go through, but GPS synchronization is really the foundation to limit self-interference, which I'll describe more in a moment. and to provide a very scalable foundation for deploying and growing the network. Self-interference, really, we talk about external interference for eFortify, which would be devices which are not under your control, they're not in your network, and yet they're transmitting on the same or adjacent channels and creating interference for your network. Self-interference is what happens where you have your own equipment interfering with other pieces of your own network. So typically we see this either subscriber modules interfering with other subscriber modules or access points interfering with other access points. So we address the access point to access point self-interference through GPS synchronization, and we do that by each access point contains a GPS receiver. They use the GPS timing reference to essentially schedule all of their transmit and receive periods to that GPS timing reference, and all of the access points in that area sending and receiving their transmissions at the same time. If you're sending at the same time as all the other access points are sending, then you avoid the self-interference issue. It's only if you had an unsynchronized network where you would have one access point transmitting at the time when another one is receiving on the same or nearby channel, which then creates a lot of self-interference.
So Alex, can you clarify something? So you gave a little bit about how GPS sync works, but how is that different from like frequency reuse, and how are they each beneficial?
So GPS synchronization and frequency reuse are kind of almost two sides to the same coin, if you will. So what we're trying to do with frequency reuse is be able to essentially reuse the same channels across the network, rather than, say, if you had a 4-sector tower, let's say you're trying to provide 360 degrees of coverage through 4 90-degree sectors, right? So with equipment that doesn't implement GPS sync, you would need to have a separate channel for each of those sectors. So you need 4 channels for that tower, essentially. So
as opposed to 2.
Yeah. So what we can do is frequency reuse. I like to say that frequency reuse is enabled by GPS sync, because really without GPS sync, you're very constrained in the amount of frequency reuse that you can do. So, in fact, I have a slide discussing this a bit better than I can at the moment, a bit later on. But essentially, with a GPS sync setup, because your access points are all transmitting at the same time, and you avoid that self-interference issue that I described, then you're able to reuse the same channel back to back. So the two, if you think of that 360-degree coverage made of 4 90-degree sectors, the 2 90-degree sectors that are back to back to each other, those can each use the same channel.
Right. Perfect.
So,
thanks.
I don't know when you want to do questions in this as
we
go
could just
along,
do them
or?
as they come up.
Okay.
But we've also found that GPS sync helps with jitter, latency, and packet loss. Might just be me, but it seems way more predictable than traditional Wi-Fi.
Yeah, so that's actually a pretty common finding, and that's really due to both the use of a deterministic MAC scheduler layer in ePMP, which Wi-Fi doesn't have. For instance, traditional Wi-Fi is a contention-based network, which will say each device that wishes to transmit on the network will say, hey, I need to transmit something. Is the spectrum clear at this moment for me to transmit? If it's not, I will wait X period of time and then try again. So for outdoor applications, that doesn't work so well, because it's very unlikely that, across, say, a 5-10 kilometer network segment, that you're going to have absolutely no other devices transmitting. So what we do in ePMP is we have a deterministic MAC, as we call it, which says, I don't really care what else is happening in the spectrum at the moment. I need my network to operate. Outdoor conditions are different to indoor conditions that Wi-Fi is designed for, so I will keep transmitting. And it's very true that GPS sync does help with jitter, latency, and packet loss, primarily because you're avoiding that self-interference that's caused as well. So you avoid a lot of the jitter, latency, and packet loss with a combination of eFortify and the deterministic MAC layer, and then you also put GPS synchronization on top of that, and it's another layer of protection against those issues as well. Great.
We'll take one more question on this topic for now, and we could answer more at the end. But Is GPS sync only applicable for point-to-multipoint?
So no, its main application would be point-to-multipoint, but we do see some deployments with point-to-point, which incorporate GPS sync. The ePMP Force 110 PTP is a PTP link which can GPS synchronize with other GPS synchronized products. And some other Cambium products also have PTP sync and various other synchronization mechanisms, even for PTP links. Depending on your tower setup, it can still be very useful to synchronize PTP links, although the main application is for a point-to-multipoint sector, multiple sectors on a single tower within an area. Cool. So just to move this particular slide along, so rate adaptation. So this is another part of ePMP technology that provides a lot of benefit for real-world deployments. So essentially, whilst we do everything we can with eFortify to prevent the network suffering from a great deal of interference, if it ever does, what we do is we use rate adaptation algorithms. So if the noise is too high at a particular moment for a given ePMP subscriber module, this is all done on a per subscriber module basis, then we adjust the radio algorithms in terms of the modulation mode and coding scheme down to a more robust mode. So this lets us keep the wireless link up even though we may not be getting the maximum amount of throughput possible if we had no interference, but if we stayed at that higher throughput, more fragile modulation mode, then we would probably lose a lot of data and potentially lose the link itself. So we dynamically adapt the modulation encoding scheme used for each SM in very fast time intervals constantly as the network's operating to make sure that it stays providing the highest reliable throughput that we can achieve. So moving on. So this is a bit of a follow-on to our discussion a moment ago about frequency reuse. So you can see what I was attempting to describe is the top site. So we have, say, the tower in the middle there providing 360 degrees of coverage, and then each one of those squares is a 90-degree sector. And you can see with frequency reuse, we can reuse those two channels, channel A and channel B, much better use of spectrum than if we had to use 4 separate channels for that one site. And you can see in the one below that, if you have a much larger network that's fairly close to your original tower, you can get by with 4 channels as opposed to a much higher number that you require otherwise. So a little bit about the deterministic MAC that I talked about. So MAC would be medium access control, but we usually refer to it in ePMP's case as an air fairness adaptive scheduler. So we talk about air fairness because I think it's a good way to explain this concept. So in other systems and also in traditional Wi-Fi, when it comes to scheduling the individual subscribers to transmit and receive data, what happens is that it's primarily based on throughput. If a subscriber has, say, a megabit of data to send, let's say those subscribers in the bottom left, A, B, C, D, E, and F, have 1 megabit of data to send each. If each one of those subscribers are operating at the highest modulation scheme, giving you great throughput, let's say each of them can operate at 100 meg at that point in time, it's very fast to get that 1 megabit of data from each of those subscribers. You don't have much of an issue with doing that. As long as you have a fairly small number of subscribers, typically below 20, that scheme works pretty well. However, if you go above 20 or so subscribers, or one of those 20 has, say, a poorer signal level than the other subscribers, let's say one of them has some foliage in the way, maybe he's further out, he's slightly misaligned, whatever the issue may be, but he's not operating at the highest throughput that all the other subscribers are, he starts to drag down the performance of the rest of the sector. Because let's say everyone else is operating at 100 megabits per second, let's say he's operating at 1 megabit per second for a worst case kind of scenario, everyone else has to wait until he's finished very slowly transmitting his 1 megabit of data. So that slows everyone else down. The more subscribers you add to that kind of system, the worse it gets, essentially. So we took a different approach with ePMP in that we have almost a time slot allocation type system. So we say to subscriber A, you have 5 milliseconds to transmit data. Then we say to B, you have 5 milliseconds, so on. So what this ends up with is that the highest performing subscribers still perform as you would hope they do with quite high throughputs, but the lower performing subscribers don't impact everyone else to the extent that they do with non-air fairness systems. So the subscriber with low throughput, he's always going to have low throughput, but with our system, he doesn't impact everyone else. He gets, a reasonable amount of data up. Of course, he's not going to be performing the same as the other guys, but he doesn't derail everyone else throughout the whole network.
Quick question, Alex. Is that only available when GPS sync is active?
No. So with any ePMP link setup, point-to-multipoint setup, we use this air fairness scheduler. It just makes more sense to think of it in the context of GPS, because then we have the advantages of synchronization that we talked about as well.
Okay, cool. And does that cause packet loss to the slower FMs?
So depends what application you're talking about. I would say fundamentally no. If you're thinking about, for instance, someone streaming a video, for example, and they are, say, streaming a video which requires 2 megabits per second, and I've said this guy's only connected at 1 megabit per second, and we're using this time slot system, essentially he's not any worse off than he would be in terms of practical application use, and if he'd have had 50 seconds to transmit his data rather than this 5 milliseconds. We're able to move very quickly between all the SMs. That's how we're able to support up to 120 subscribers per access point. But for the kind of subscribers that are in a very bad signal, they're not really any worse off through our testing than if they were with a system based on bandwidth rather than time. Typically, if the guy is not receiving a good enough signal to meet the throughput requirements of his application, then really that has to be handled in the application layer. For instance, the video service has to downscale the resolution until his signal returns to acceptable level. That was somewhat a long-winded answer to that question, but I hope it made sense. Short answer, no. Yeah. So moving on from this one. So I talked a little bit about eFortify and things like that. This is somewhat of a simplistic graph, but hopefully gets the point across in that we put side by side an ePMP connection next to a Ubiquiti connection, not attempting to call out anyone in particular, but being the best known vendor, it typically is the point of comparison. So we had a artificial level of signal interference pumped into both links in concert at the same time. So you can see that in a link with ePMP's eFortify technology, by the time we got to moderate high interference, we were still operating around 95 megabits. And when you got to very severe interference, and I'll be honest, that level of interference was much more than I would hope you would see in any reasonably deployed network. The headline for me is that as opposed to having no link, you could still potentially have a 30 megabit per second throughput link. But rather than kind of dwell on the comparison, I'd like to move on to some of the more advanced technologies that help build on top of what we've already talked about for ePMP. So just a quick note, a bit more about the spectrum usage and why that's important. So we talk about GPS synchronization and making the best use of the available spectrum. So in unlicensed spectrum, the spectrum that you have is pretty much all the spectrum you're ever going to get. I've yet to see somewhere on the planet where I've been so far where we've had a significant lowering in interference in unlicensed spectrum. It seems pretty much every day that wherever you go, someone else is putting up a new network, or there's a new outdoor Wi-Fi network, a new WISP starting up nearby that just raises that noise floor a little bit more for your network in 5 or 2.4 gig.
Hey Alex, do you mind if I derail you for a second?
Of course I do.
Yeah, but do it. So I'm sure you're going to get to it, but so obviously, ISPs, they might struggle to get customers to pay more. So with these features that you're about to talk about, how would this help that?
Yeah, I mean, that's at the end of the day, that's really what it's all about, right? So thank you for kind of bringing me around to that. So let me skip through a couple of these bits and really get to some of the other stuff that really enables the WISPs to be able to make more money from their customers, right? So as well as just being able to provide a reliable connection, which also helps when you're trying to get people to pay for a service, this level of functionality that we have in ePMP for supporting what we call advanced services or advanced port for network services, as I've written it here, also helps. So we're talking about applications such as voice over IP, video, IPTV, and there's more I'll get to in a moment. But how we specifically address these applications in ePMP technology is we have over-the-air QoS, and we have 3 distinct queues, one of which is purpose-built for voice over IP traffic. So we deliver very jitter-free voice over IP traffic, which over wireless connections, even cellular connections, is still a challenge. So voice over IP would let the network operator essentially charge for not just internet service but also landline telephone service. So that's another $5, $10 a month they can potentially make from each user. Another thing that we implement is, I talked about the rate adaptation. It also functions specifically differently for voice traffic to minimize jitter and try and target zero packet loss. So video surveillance, when we talk about what you can use ePMP for, even as a wireless service provider, don't necessarily just think it's only for residential internet access. We've got a lot of CCTV video surveillance deployments. For instance, you could provide video surveillance to a city or a large outer area such as a supermarket, car park, things like that. We see a lot of service providers branching out into that because for comparatively small investment in installation time and equipment, they can make pretty good recurring revenue as video surveillance providers as well with ePMP, and I've got a very good example of that coming up soon. So we also perform internet group multicast protocol snooping to restrict traffic of multicast video to specific radio links. If anyone has ever dabbled with multicast video, you will know that unless you have specific multicast provisions in your network, it basically functions exactly like broadcast and kind of defeats the point, to be honest, because multicast transmissions should be restricted to only those users that have signed up to that group to watch that video. But if your network equipment doesn't know who those users are, it has no choice but to flood that high throughput traffic to every user. So we handle that in ePMP by snooping on the requests that the end devices send back to the application that say, hey, I want to join this group and watch this video, and we restrict that video traffic to only those radio links. So IPTV, I kind of talked about that a little bit, but there's some other applications that we have here. In fact, IPTV is a good one I'd like to talk about a little bit, but I have a specific case study on this I'll get to shortly. But that's a very good one for service providers to be looking at to increase the amount of revenue they can get per user and also the stickiness of their service as a whole. An interesting kind of fact point I find from talking to operators is that whilst internet service and voice over IP service are great, and certainly people don't really want to switch away from it unless they have to or they have a very good reason to, sometimes, particularly in some areas of the world and some customers, cash collection can be a challenge with service providers getting revenue for voice over IP and internet service. Consistently, I've heard, and it's kind of funny to me, that if you cut off someone's IPTV connection, they'll pay pretty much within the day. If you cut off someone's internet or voice over IP service, they'll typically wait a week or two and kind of hope that you give up. But evidently people can't do without the Great British Bake Off or whatever people are watching these days. Anyway, so enterprise connectivity I kind of touched on a little bit earlier. If you think about providing not just residential internet access, but also business internet access. A lot of the features that we talked about in ePMP technology are very handy at doing that, because with business connections you're going to have tighter service level agreements. So the predictability that ePMP technology gives you is very valuable there. And then just a couple more that we've explored here. Wi-Fi hotspot backhaul being my personal favorite of those two.
Great. So Alex, as far as the quality of service for phone calls are concerned, what happens if there's like 50 calls at once and everything just gets overloaded? Is it able to handle that?
So, I mean, if you think about the actual traffic load from 50 voice calls, I mean, obviously depending on the voice codec that's in use, but I mean, you know, many voice codec calls today are still using, you know, 64 to even 128 kilobits per second is a fairly high data rate for a voice call. So, to be honest, I think unless you're doing a big, you know, trunk of phone calls, you would struggle to overload the capacity of an average ePMP connection. But specifically with the QoS regarding this, specifically with the QoS regarding this level of voice calls, our specific QoS scheduler that we talked about in the second bullet point there is made to handle all VoIP traffic that comes in regardless of the volume. So we have a dedicated priority queue ahead of all other traffic for voice over IP, which minimizes the jitter and latency regardless of the number of calls going over the system at that particular time. 50 phone calls I would not expect to be any issue for an ePMP system. As I said, in terms of traffic load, that's still a fairly small amount of traffic load compared to, you know, for instance, bulk data or video traffic, and then matched with our automatic prioritization of VoIP packets and the specific scheduling for voice packets that we have in there, it's typically handled very well.
Oh, great, thanks. Yeah, that answers the question.
So, just moving on, I realize we're getting on in time here, so I'll speed up slightly to get to the more interesting bits. But so one thing I wanted to mention about ePMP that's also across many other Cambium Networks products is CN Maestro. So this is a cloud-managed network management system, essentially. Sorry, cloud-based network management system, which allows you to onboard, monitor, configure, and troubleshoot devices pretty much from wherever you are across the whole network.
So CN Maestro is a cloud-based solution. What makes this better than, let's say, an on-premise solution?
So I would say that we do offer both in terms of CN Maestro. We primarily position it as a cloud-based system, but there is a Network Operations Center NOC version available to be locally installed. But I would say that the advantages of a cloud-based system, and CN Maestro in particular, are that wherever you are, you're able to monitor your network. For instance, if you happen to be at home at some point, I know a lot of our service providers are quite small operations, some of them even one-man bands. So if it's just you get a call saying so-and-so's down, or is X happening on the network, my internet isn't working, you're able to very quickly troubleshoot what's going on right down to even the connected Wi-Fi devices in the home. If you also use a Cambium Networks Wi-Fi router as well, you can troubleshoot across that whole ePMP network path and say, okay, I know it isn't this, and this, and then you're able to basically make the best use of your time in terms of troubleshooting. Why is there a delay when approving and onboarding a device to show up in CN Maestro? So when we add a device into CN Maestro, there is some back-end work that happens in the server. Some of the databases need to be resynchronized with this new data and then pushed back out. We are trying to speed up the onboarding process and expect to see some improvements on that in the future. But I do apologize if there's ever a delay in doing that affects anything that you're trying to do. We try and make everything that we're doing at Cambium as easy to use as possible. And any challenges like those that you've highlighted, we definitely do our best to address. So we're working on it, but at the moment, hopefully the delay isn't too limiting for you.
Yeah, and on that note, if you do have any concerns, please post on our community page. We check that daily, and we do take your suggestions to heart.
Yeah, that's a very good point, actually. So I realize we have about 20 minutes left. I would say for some of the more pressing questions about CN Maestro, I would personally like to direct you at the moment to the CN Maestro area, as Colin mentioned, on the community forum, where we can answer all the questions there, just purely so I can get to the end of this one about ePMP. So my apologies for not being able to answer every question at the moment, but if you post them on the community forum in the CN Maestro section, they'll be sure to be answered very quickly for you. So just moving on, a little bit more about the kind of summary of the ePMP advantages that we talked about. Just going through this a little bit quickly to get to some of the other interesting technologies that we implement in ePMP. So these are all things that we've discussed. So just a couple of quick use cases. I mentioned an IPTV network. So this is a large service provider in Serbia. They're actually much larger than this now and have around 40,000 subscribers on wireless in Serbia. They have an end-to-end IPTV solution. They replaced their existing wireless solution due to the performance of ePMP under video applications, the ability to support much higher subscriber density, and they found that with other solutions the amount of lost data and then retries was somewhere around 30% of their total network capacity, which was quite a waste of bandwidth. So here's a couple of images of the deployment as we go along. These numbers are out of date for the subscriber count. I do apologize, it's much higher than that at the moment. But you can see the basic setup that they have here is, you know, they have 95% residential, 5% enterprise, and that's the internet service packages they offer.